Okay, so from the GUI, we're going to go to the main equipment tab where we're starting. And then we're going to go down under Fabric Interconnects. We're going to go down to the Ethernet ports. And if we just click on the fixed module, what we should see is what ports are currently being used, what ports are currently disabled, or what ports are in the admin down state. Okay, so either admin down or link down. This kind of dark brownish color, this means that these interfaces are unconfigured. So physically, ports 1 and 2, these are the ones that are going down towards the chassis. Interfaces 3, 4, and 5, we're going to be using these in the port channel. Okay, so interfaces 6 and 7, I'm going to disable this. So right-click and disable. Okay, I want to turn off port number 6, yes. And then likewise on port number 7, disable, yes. And then the same thing on Fabric Interconnect B. So let's close up Fabric A, let's go to Fabric B. And right now we see interfaces 1 and 2 up. Okay, if we hover over these, it says the type is server, so that's going down to the chassis. Interface number 3 is network. We're going to configure ports number 4 and 5 also as uplink, okay, which is going to make those network ports. Okay, next step is that we're going to go to the LAN tab and we're going to configure 2 different LAN port channels. So we're under LAN, which is the default place in the browser. And then we're going to go under Fabric A, under port channels. Right now we don't have any port channels configured, so we're going to right-click port channels, we're going to create, and we give it a number. Okay, so we'll say this is port channel 101. And let's say the name is VPC 101, 101 to 5K1 and 2. Let's see if we can, no, that's too long. Okay, so let's say 5K1 underscore 2. So next, and then we choose what ports. So we want ports 3, 4, and 5. So just control click, move them over to ports in the port channel, then click finish. Okay, so pretty straightforward from the GUI point of view. Okay, right now it says that there's going to be a problem with the servers or the service profiles when we go to actually apply this. It says there's going to be an issue with one of the virtual NICs that we failed to find any operational uplink port that carries all VLANs of the VNIC. The VNIC will be shut down, which will lead to traffic disruption on all existing VLANs of the VNIC. Basically, what this means is that when the UCS goes to make its pinning decision, it looks at first what VLANs are we trunking from the Fabric Interconnect southbound to the actual server, okay, down to the blade. So this is going to be controlled under the service profile, under the VNIC, and then what VLANs are a member of the VNIC. So ultimately what it's trying to do is to find a match between the southbound links to the server and the northbound uplinks out of the FI to make sure that there's a single port that is matching all VLANs. So what I mean by this is that if we were to go back to our logical diagram or physical diagram, I should say, and what we're going to see is that we have 2 different servers. Okay, so one of them is running VLAN 10, one of them is running VLAN 20. Then from the Fabric Interconnect point of view, we need to find a single uplink that is carrying VLAN 10, and we need to find an uplink that's carrying VLAN 20 in order to make this pinning decision northbound. Now, we did talk about in the previous section the disjoint layer 2 design, and we are going to revisit this as we talk about in-band management. But the key point here is that if VLANs 10 and 20, we're going to different physical switches that are not interconnected east-west. We would need to make sure that the VLAN allowed list for VLAN 10 is pointing towards the VLAN 10 topology, VLAN 20 is pointing towards the physical VLAN 20 topology, and then the pinning decision would automatically choose the correct uplink based on the VLAN memberships. So more specifically, what I mean by this is that if we were to have another physical switch, let's say that we're also going to 5K3, then to 5K1, we were trunking only VLAN 10, and up to 5K3, we were trunking only VLAN 20. We would see that the virtual NIC that's using VLAN 10 would automatically pin up to 5K1, and then the virtual NIC that is using VLAN 20 would automatically pin over to 5K3. So this means that the pin group is not required in order to solve the disjoint layer 2 problem. It's actually unrelated to disjoint layer 2. The only thing the pin group is solving is to dedicate bandwidth for an individual blade. So let's say, for example, I have 4 physical uplinks from the fabric interconnect to the northbound switches. I have 2 different design options. I could either channel all of them together in a 4 by 10 gig channel, so a 40 gig channel total, or I could use 4 individual links and then let the servers decide how they're dynamically pinning. Now, what this allows you to do is to take, let's say, blade 4, pin it to link 4, take blade 3, pin it to link 3, blade 2 to link 2, etc. And then we're essentially guaranteeing the oversubscription ratio of the blades to the northbound network. Disadvantage of that design, though, is that if the physical link goes down, we cannot repin automatically to another link unless the VLAN is actually allowed. Okay, so in this particular example, we don't really need to make a pinning decision because there's only one logical port channel. Ultimately, the system still makes the decision, but the decision is the same result over and over and over, so we wouldn't need to deal with disjoint layer 2. Okay, that's why they talk about this in the technology design guide, because it's by far the simplest option for doing LAN connectivity, is that from the FI's point of view, they basically just have one interface going northbound, and all of the VNICs, so VNIC for VLAN 20, VNIC for VLAN 10, all of these are going to pin to the logical port channel. And then we're going to assume that both 5K1 and 5K2 have both VLAN 10 and 20 trunking down to the FI. And then assuming that that's the layer 3 gateway, that we have the SVIs configured, we have some sort of routing protocol in order to actually route the traffic towards the northbound LAN. Okay, or more specifically towards the northbound WAN, I should say. Okay, so ultimately this output should change. Okay, so let's go back to the GUI and let's go under the, actually not the GUI, go back to the CLI and let's look at just the show interface status. Okay, on both of the FIs. So let's say terminal with 511, then show interface status, and we should see that there's a new port channel that is going to be going upstream. Okay, so the system has generated a couple different port channels automatically. So we have 153 or 1153, 1288, etc. Okay, some of these are connected, some of them not. These are going to be referring to the ones that are going down to the blades. So if we show interface port channel 1153, we should see that this is bound to one of the downstream server slots. Okay, specifically it says members in this channel is Ethernet 1.1, Ethernet 1.2. These are the server ports that are physically going to the chassis. So if we look at the running config on that port channel, we should see that this is the FEX fabric port, same as we would have on the 5Ks going down to the 2Ks. Okay, then the other interfaces that were created, for example, number, let's say 1290, show interface port channel 1290. It says this is bound to interface Ethernet 1117, 1119. And then if we show interface E1117, this should tell us here what particular, actually I'm not sure if this shows from the CLI, but we can map this to what particular slot this is physically referring to just by counting the number of ports. Okay, so physically, ports 1, 2, 3, 4, these are going to blade 1. 5, 6, 7, 8, those are going to blade 2. 9, 10, 11, 12 is number 3. 13, 14, 15, 16, number 4. 17, 18, 19, 20, that's going to blade number 5. So in our case, it was number 17 and 19 that were channeled together. So physically, port channel number 1290, okay, which is Ethernet 1117, 1119, it means that this is going down to blade number 5. Okay, that's going to be 17, 18, 19, and 20. Now, for this configuration, there's nothing that you can change about that because the port channel number is going to be based on where the physical server is plugged in. So if you want to move what uplink it's pinned to, essentially you'd have to physically pull the blade and then move it to a different slot. In our case, we don't really care about this, though, because the physical uplinks that when we look at the show run interface E11 to 2, so the uplinks from the chassis to the FI are in a port channel. So regardless what the physical blade pinning to the I/O module is, the end result is that we're going to load balance the traffic from this port channel. Okay, what we now need to create is the uplink port channel that's going to go to the 5Ks. Okay, so again, we're doing this under the LAN tab. So I'm going to go back to the HTML5 interface. So we created this under port channel 101 under fabric A. We now need to do the same thing under fabric B. So let's go to fabric B, then under port channels. Okay, and unfortunately, the UI for this, you can see, is super slow sometimes, even when we're on the connected LAN segment. So let me try clicking off and back on. Otherwise, if you see the HTML5 interface hangs, just use the Java interface. Okay, they pretty much accomplish the same thing. Okay, let me try reconnecting here. Okay, so let me kill the HTML5 interface. Let's go over to the Java one. So if you do see this hang from the rack rentals, what you need to do is go to the task manager and then kill the Chrome process. Okay, so let's try the Java interface now. So we're under UCS manager, and then we're under the LAN uplinks manager. Okay, so let me close LAN uplinks. And let's go back to LAN. Then we're going to go under fabric B, and then under port channels. Fabric B, port channels, right click, and then we're going to create a port channel. Create port channel. Okay, so this is going to be port channel number 102. 102. And the name, let me see if I still have the same string. No, I don't. Okay, so this will be VPC 102 to N5K1 and 2. Okay, VPC 101 and 5K1 underscore 2. Okay, then next we're going to pick the physical ports. So while we're on break, I'll reboot the virtual machine. Sometimes that'll speed it up, but as you can see, unfortunately, it's just the nature of the Java interface. So ports 3, 4, and 5, move these over, then finish. Okay, that should create the port channel. So let's go now back to the CLI and look at the show port channel summary. We should now see port channel number 102. Okay, this is right now it's interfaces 3 and 4. We should see the 5th interface be added there shortly. And right now they're in the down state. So if we look at the show run interface port channel 102 membership, same output as we would on 5K or 7K. And so we see a regular Ethernet port channel. It's running LACP mode active. And the trunk allowed list is all of the VLANs we have created. So VLANs 1, 10, and 20. Okay, so now our next step is that we need to configure the VPC on the 5K side in order to match down to the fabric interconnects. So I'm going to do this fairly quickly. We've done this in a number of examples before. It's just a standard VPC config, so nothing special about the virtual port channel config on the 5Ks. So first, let's look at the show run VPC, and we should see that they're not configured. Okay, so we're going to go to global. We're going to say feature VPC, feature LACP. We're going to create the VPC domain. We'll say this is domain number 1. The peer keep alive destination is going to be the management IP, so 192.168.0.51 and 52. Okay, so 5K1 is pinging 50, or excuse me, 5K2 is pinging 5K1. 5K1 is pinging 5K2. If we look at the show VPC, we should see that the peer is alive. Okay, so we know management connectivity is working. Okay, then we configure the peer link. So let's say interface E1 3 to 4 is going to be a switch port. Switch port mode is trunk. It's going to be a channel. Channel group, we'll say 34, mode active. And then on interface port channel 34, this is the VPC peer link. Okay, this should also change the network type, the spanning tree network type to, or excuse me, the spanning tree port type to network. Okay, that's enabling bridge assurance. If we then look at the show VPC, we should see that the peer link is up. Okay, so in a second when they negotiate, let's look at the show interface E13 to 4 status. Okay, is connected. Let's look at the show port channel summary. Port channel is up, so if we show VPC, we should see now peer adjacency is formed. Okay, so now we have the very last step, which is going to be the trunk that's going down to the UCS. Okay, so let's make sure that we have the VLANs created. So we have VLANs 10 and 20. And then we're going to trunk these down to the UCS, okay, as a channel. So let's look at the physical diagram. On 5K1, this is going to be ports 9 and 10 for the first VPC. So on 5K1, let's say that interface, actually let's say default interface E1, 9 to 11. Okay, same on 5K2. So we're starting from a blank config, 9 to 11. Okay, so interfaces E1, 9 to 10. These are going to be in channel group number 1. Okay, mode is active. Okay, mode active here being the key operator. At the UCS Fabric interconnects, you cannot disable LACP. So LACP always run as mode active on the FI to northbound. You need to make sure that you're configuring either channel mode active or channel mode passive to negotiate LACP. Okay, it doesn't support PAGP negotiation or static channels. Okay, so channel number 1 is mode active, and then on port channel 1, we'll say that this is a switch port. The switch port mode is trunk. The spanning tree port type is edge trunk. Okay, key point there. And then this is going to be a VPC. Okay, that's VPC number 1. Okay, interface 11 is going to be the other port. So this is going to be channel group 2 mode active. Interface port channel 2 is going to be a switch port mode trunk. Switch port mode trunk. Spanning tree port type is edge trunk, and then on port channel number 2, this is a VPC. Okay, VPC number 2. Okay, so on the 5K1, let's look at the show run interface port channel 1 membership and show run interface port channel 2 membership. Okay, this we can now just copy into Notepad, change the numbers around to match the other 5K. Okay, so on 5K2, we're going to have port channel 1 and port channel 2. Okay, so same as the other 5K. Okay, both of these are VPC, so VPC 1 and 2 respectively. Then the membership, ports 9 and 10 will be in channel 2. Port 11 will be in channel 1. Okay, so basically the same config except some different port assignments as we're going down to the access layer. Okay, if we now look at on both of the switches, the show VPC, we should ideally see that the channels are negotiated. So actually first let's look at show port channel summary. This will tell us, did LACP negotiate? Okay, which it did. Okay, the ports are in the channel. Same should be true over on 5K2. Okay, so we see 11 is in VPC number 1, 9 and 10 are in VPC 2. If we then look at the show VPC, pipe no dash more, we see that now port channel 1 and 2 are up, and same should be true from 5K1's point of view. Okay, so we're forwarding all of those VLANs. Note that additionally, we're forwarding VLANs 101 and 102 that are different between the two VPC members. Normally, this would count as a type 2 consistency error per the VLAN, that we're mismatching what VLAN numbers we're chunking down to the members. But this is an exception here because VLANs 101 and 102 are mapped to FCOE vSANs. So we are allowed to do a SAN A, SAN B separation on the member ports. Now, in our particular case, since we're not running FCOE, we're running native fiber channel, what I'm going to do is to prune these numbers from both of the port channels. Okay, because we don't need to send any of the FCOE control plane down to the FI. So I'm going to say on interface port channel 1 and port channel 2, switch port trunk allowed VLAN remove 101 and 102. Okay, if we now show VPC pipe no more, we should see that only VLANs 1, 10, and 20 are being forwarded on the members. Okay, now from the FI's point of view, the final result of this should be when we look at the show pinning for the border interfaces, we now see that we have port channel 101, and all of the VETHs, so both for blade number 4 and number 5, are automatically pinned to the logical port channel. Okay, same should be true on Fabric Interconnect B. If we look at the show pinning for the border interfaces, we see port channel 102. Okay, now let's test this actually down to the OS. So let's go back to the GUI and let's see, is the KVM still open? Okay, it looks like it is. So we have our two servers that are in VLANs 10 and 20 respectively. Okay, we have the 10 network and we have the 20 network. So the IP addresses are 10.0.0.102 and 20.0.0.101. So let's go back to the 5Ks and let's see if they have the VLAN interfaces. So let's show run interface VLAN 10, show run interface VLAN 20, and both of these should have both VLANs. Okay, if we look at the show MAC address table for VLAN 10, we should see that we have the virtual IP address or virtual MAC address for the HSRP group, and the supervisor is listening for this. So it means that this guy is the active forwarder. Okay, likewise on 5K1, we should see we have the virtual address, and it says the supervisor owns it. The reason why is that when we're doing a VPC, HSRP automatically becomes active-active. So even though from the control plane point of view, when we show HSRP, one of them is going to be active, one of them is going to be standby. From the data plane point of view, whenever a packet comes in from the VPC, we look at the destination MAC address, it matches the virtual MAC of the HSRP group, then we're going to route that traffic northbound. So essentially, regardless of whether we're going on Fabric A or Fabric B, 5K1 and 5K2 can both route traffic for VLAN 10 and 20. So ultimately, our final verification would be to ping the end hosts. Okay, the end hosts in this case are going to be 10.0.0.102, okay, which we can reach, and then 20.0.0.101, okay, which likewise we can reach. So 5K2 is able to reach both, 5K1 likewise able to reach both. So if we look at the show MAC address table for VLAN 10, we should see that we're going to have a entry for the hypervisor. Okay, so if we look at the show IP ARP, we see that 10.0.0.102 is mapping to the MAC address B500.008F. So let me ping this again, ping 10.0.0.102. Then let's show MAC address table, pipe to include 008F. Okay, we can see that we're learning this dynamically on port channel number 1. Port channel number 1 is the VPC member port that's going down to Fabric Interconnect A. Okay, so this tells us that that VNIC is pinned to Fabric A as opposed to be pinning to Fabric B. If it was on Fabric B, then we would see it learned on port channel 2, which is VPC going to Fabric B. Okay, likewise, if we ping the VLAN 20, so let's ping to 20.0.0.101. We then look at the show IP ARP to find the MAC address. MAC address is B500.0.0.1. Let's show MAC address table pipe to include this guy. We should see this as a dynamic entry in VLAN 20, which we do. And we see likewise pinned to port channel 1. This means that this NIC as well is going to Fabric A. And again, key point here is that from the Fabric Interconnect, when we looked at the show pinning for the border interfaces or show pinning for the server interfaces, okay, looking from the other view, notice that all of the exit interfaces are pinning in the same direction. That we're going port channel 101 on the A fabric, we should see that we're using port channel 102, show pinning for the server interfaces. We should be using port channel 102 on the B side. So again, by far, this is going to be the simplest LAN connectivity design because we don't need to deal with any disjoint layer 2. We don't need to deal with the VLAN allowed list. We don't need to do any LAN pin groups in order to assign the VNICs to the northbound links. Essentially, each fabric just sees one logical port channel, and it doesn't know that it's load balancing traffic to multiple physical switches because the 5Ks are spoofing the LACP system identifier as part of the VPC. If we were to look from the Fabric Interconnect and show LACP neighbors, we should see that on ports 3, 4, and 5, we see the same partner ID. There we see the same LACP system ID coming in all 3 of the links. So from the FI's point of view, LACP says, okay, it's going to the same port or going to the same switch. Let's channel all of these together, and then we're going to load balance the flows for the individual VNICs. So just like we can on the 5K or the 7K, we should be able to look at the show port channel traffic. And this is going to tell us the northbound distribution of traffic leaving the system. Okay, and specifically, we're looking at channel number 102. So we see transmit unicast, it's always using one physical port. And the reason why is that we don't have diverse flows that are going to multiple IP addresses within the Blade system. So if we were to boot up more servers and then start to actually send traffic to them, like let's say, web browsing, whatever, we should see ideally from the FI's point of view that the outbound traffic, the TX unicast, should be somehow fairly equally distributed between the 3 interfaces. But right now, since the only thing we did was ping, just the management IP, that happens to be landing on the same upstream link. Okay, same thing on Fabric Interconnect A. Let's look at the show port channel traffic. And we should ideally see for port channel 101 that somehow the load is split. Okay, so first interface got about 5%, second interface got about 95%. But we can tell at least that it is being used. So load balancing is correct. Okay, if we look at the show port channel load balance, we can see that for IP traffic, the UCS is using the layer 2 and the layer 3 header. Okay, so source destination MAC address and source destination IP. And as far as I know, this is not a modifiable parameter. You can't change the load balancing method of the FI.